All right, so now we're going to look at the limit comparison test. And the limit comparison test is going to go like this. So you will still need that the coefficients be positive, but you will not need, so you're going to have your coefficients, or the summands, will satisfy such that the AIs and the BIs are all non-negative. So you do need them to be positive for that. And you will say that the limit, let's let L be the limit as n goes to infinity of an over bn. And that L can be several things. So if, I can write it here still, if 0 is strictly less than L, strictly less than infinity, then this is the one that is very useful. Then an, the sums rather, the series, and bn, series infinity, both converge or both diverge. All right, so whenever you have that the limit is not 0 or it is not infinity, so it just gives you a number, of course being defined, I'm assuming it's defined and it's a number in between 0 and infinity, then you have that the series, both of them converge or both diverge. What does that mean, or why is that the case? Well, what that's telling you is that an and bn grow roughly at the same rate. So if both go out to infinity, both will diverge together. And if one goes to doesn't go to infinity, the other one will not go to infinity either. Now there's other options that you can have, and they're not really that useful, but you can at some point use it. So if the limit happens to be infinity, so what does that mean? That an grows much faster than bn. But so if an grows much faster than bn, and that should have been a comma or just that, and oh goodness, let's erase as one should. So if L is infinity and bn, or the sum rather, the series, diverges, so does an. Because an is growing faster than bn, so because it's going out to infinity or a faster rate, so if bn happens, if the sum of the bn's or the series of the bn's happens to diverge, then the series of the an's will diverge as well. Sorry, I had a little mistake here, so I went ahead and checked it. And so what happens is that if this limit goes to 0, then that tells you that an is going to be smaller than the bn in their growth rate, let's say. So that then tells you that if the larger one diverges, then the smaller one, the larger one converges, rather, the smaller one converges as well. So that will be the part of the limit the part of the theorem that I needed. But this is the one that we're going to be using the most. So let me go ahead and give you a couple examples, and then we will finish the video right there. All right, so let's do these examples here quickly. So the first one, I'm going to compare it, as we had said before, to the series from n equals 1 to infinity of 1 over n. This is the one I did in the previous video that didn't quite work with the direct comparison test. So I'm going to do it with the limit comparison test. So what you do is you do the limit as n goes to infinity. And you grab this, call that your an. Doesn't matter. If you're going to use the first part of the theorem that I left here, it doesn't matter which one is an and which one is bn. And instead of dividing by 1 over n, I'm going to multiply times its reciprocal. So that is just going to allow me to compute the limit a little bit easier. At least I don't have to write a whole lot. I'm going to have n squared. N goes to infinity. Sorry about that. I'm going to have n squared over n squared plus 1. And the limit is 1, which is not 0. And it's not infinity. But I know this one diverges. So I know both diverge. Both series diverge. A little bit summarized, but I don't want to rewrite a whole lot and make the whole board. Now, this one right here, oh, this one is not very nice. I mean, it's nice, but it's not. Anyways, no, this one is a bad example, actually, because this one you could do, I'll leave it because it's actually useful to tell you that whenever you have something that is of degree roughly 1 here, and this one is roughly 1 as well, what you could do is just do the divergence test and say the limit as n goes to infinity of the anth term. So not a comparison test, just straight up a divergence test. You can verify that this limit will be 1, which is not 0. Therefore, this series diverges. So that one is, this is the divergence test. This is not the limit comparison test, because when you take the limit as n goes to infinity of just an, and if that is not equal to 0, you know that you have divergence right away, that your series diverges. All right, so here I'm going to compare it to the sum of n equals 1 to infinity of 1 over n squared, which converges. And I'm going to use that other part of the theorem I told you that we don't often use, but this is a time when you would actually use it. So let's take a look at the limit as n goes to infinity. And for these ones, it does matter what order you pick it. So I'm going to start with my an being e to negative n. And then grabbing this, writing the reciprocal of this as n squared over 1. So dividing by this bn, but I'm going to multiply it like that. And so what I'm going to end up with is the limit as n goes to infinity of e to negative n, which is going to give me an e to the n in the denominator. And this one, I don't have a lot of room, but by L'Hopital's rule, you can do it one time, because this goes to infinity, this goes to infinity. I get 2n over e to the n. Still is infinity over infinity. I get then 2 over e to the n, which ends up going to 0. So now, notice that I have here that this limit goes to 0. So this series is decaying much faster than this one. But I know this one converges, therefore both converge. So that gives me that n equals 1 to infinity of e to negative n converges. Now, I will point out that not all the textbooks have that second part of the theorem. Most textbooks will only have this part. So this series over here, you would have to do with another method. You wouldn't do the limit comparison, but I added it just for completion, as some books actually do include that the part of the theorem that I wrote over here. All right, so that'll do it for this video. Thank you for watching, and I'll see you in the next one.